Hey everyone, and welcome. Today we're going to tackle a programming challenge that, here's the twist, is secretly a clever counting puzzle. It's one of those perfect examples of how just looking at a problem from a different angle can unlock a really simple and beautiful solution. All right, so before we even think about a single line of code, let's just toss that aside for a second. Let's reframe this whole thing. Forget programming. We're just going to think about arranging numbers. It's a simple, how many ways can you do it kind of problem. So here's the puzzle at its heart. I give you three numbers, 1, 2, and 3. Your job is to arrange them into different structures. Now, there's a catch. There's one single, simple rule you have to follow for every arrangement. So, how many unique structures do you think are possible? Go on, take a guess. The answer is 5. Now, if you guessed 3 or maybe 6 because you were thinking about permutations, hey, you're in good company. That's what a lot of people think. The fact that the answer is 5 is, well, it's kind of weird, right? It tells us there must be a very specific constraint at play. So, what is this mystery rule? That rule is the definition of something called a binary search tree, or BST for short. And the beauty of it is just how simple it is. You pick a number, any number, to be the root. That's the top of the tree. From there, anything smaller than that root has to go to the left. Anything larger has to go to the right. That's it. That one rule controls everything. Okay, so how on earth do we find those 5 different structures for the numbers 1, 2, and 3? Honestly, the most intuitive way to start is to forget about fancy formulas and just start drawing. Let's solve the simplest versions of this problem first and see if we can spot a pattern. Let's do a little warm-up. If you've only got one number, so n equals 1, well, there's only one way to arrange it, right? It's just the number itself. Super easy. Now, what if n equals 2, and we have the numbers 1 and 2? Okay, think about it. If 1 is the root, 2 is bigger, so it has to go to the right. If 2 is the root, 1 is smaller, so it has to go to the left. That gives us exactly 2 structures. See? We're starting to build up our intuition here. All right, now for the main event. We've got our rule, and we know there are supposed to be 5 solutions for the numbers 1, 2, and 3. Let's actually build them one by one and see exactly how we get to that number 5. Let's start by picking the number 1 to be our root. Now, according to our BST rule, any numbers that are bigger, which in this case are 2 and 3, have to go into the right branch. So what we've really done is create a little subproblem. How many ways can we arrange the numbers 2 and 3 so they also form a valid BST? You know, the exact same logic applies if we pick 3 as the root instead. All the smaller numbers, 1 and 2, they have to go into the left branch. And this creates another subproblem. How many ways can you arrange the numbers 1 and 2? Hey, wait a second, we already know the answer to that from our warm-up. There are 2 ways. So that gives us 2 more possible structures. So what's our last option for the root? The number 2, right? If we pick 2, the rule is crystal clear. The smaller number 1 has to go to the left, the larger number 3 has to go to the right. There's literally no other way to do it. This perfectly balanced tree gives us our 5th and final unique structure. And there you have it. That's the complete set. We got 2 structures when 1 was the root, another 2 when 3 was the root, and that one perfectly balanced structure when 2 was the root. So 2 plus 1, that gives us our magic number, 5. We found every single one just by drawing and following that one simple rule. Look, drawing is great. It really is. But what if I asked you to solve this for n equals 10? Or, heaven forbid, n equals 19? We are not going to sit here and draw thousands of trees. No way. This is the point where we need to shift gears from just drawing stuff out to finding that elegant mathematical pattern that's been hiding under the surface the whole time. So let's get organized and just lay out what we know. For 1 node, we found 1 tree. For 2 nodes, 2 trees. For 3 nodes, we found 5. And I've added a really important one here. For 0 nodes, there is exactly one way to do that. It's just an empty tree. Now, that might sound a little weird, a little philosophical, but trust me, accepting that an empty tree is one way is the secret key to making our pattern work. Let's go back to our n equals 3 case one more time, but let's think about it a bit more abstractly. When 1 was the root, how many nodes were on the left? 0. And on the right? 2. When 2 was the root, we had 1 on the left and 1 on the right. And when 3 was the root, we had 2 on the left and, you guessed it, 0 on the right. You see that symmetry? It's pretty cool. And that leads us to the pattern. Here it is. The total number of trees you can make is just the sum of the possibilities for every single choice of root. And for any one of those roots, the number of combinations is the number of ways you can arrange the left side, multiplied by the number of ways you can arrange the right side. Okay, let's put this pattern to the test and see if it actually gives us 5 for n equals 3. So if the root is 1, we have 0 nodes on the left and 2 on the right. That's the number of trees for 0 times the number of trees for 2. From our table, that's 1 times 2, which equals 2. Makes sense? Now, if the root is 2, we have 1 node on each side. So trees of 1 times trees of 1, that's 1 times 1, which is just 1. And if the root is 3, it's the mirror image of the first case. 2 nodes on the left, 0 on the right, giving us another 2. So what's the total? 2 plus 1 plus 2 equals 5. It works. The pattern is solid. This is that aha moment. So now we have this amazing, repeatable pattern. The next logical step is, how do we turn this into a program that can solve for any n almost instantly? Let's take a look at what this logic looks like when you write it as code. Believe it or not, this single line of code is the entire engine of the solution. It might look a little scary at first, but I promise you it's the exact same logic we just figured out by drawing. The I is our n, the j loop is basically us trying out every single number as the root, and then for each root, it just multiplies the stored answer for the left side by the stored answer for the right side and adds that to our running total. It's our pattern, just written in code. What's so brilliant about this strategy is how efficient it is. The code builds the solution from the bottom up. It calculates the answer for n equals 0, then n equals 1, then n equals 2, and so on. And it saves every result. So when it gets around to calculating the answer for, say, n equals 10, it doesn't have to figure out the answer for n equals 3 all over again. It just looks it up. This whole idea of breaking a problem down and reusing the solutions to the smaller pieces, that's a cornerstone of really smart programming. So let's zoom out. What's the big takeaway here? This whole thing wasn't really just about binary search trees, was it? It was actually a masterclass in a universal way to tackle really complex problems, whether you're coding, starting a business, or just dealing with something in your life. And this is the strategy you can take with you and apply to pretty much anything. 1. Start with the absolute simplest cases. Get some easy wins. 2. Look for a pattern. How do those simple cases build up to create the more complex ones? 3. Realize that huge, scary problems are often just a bunch of smaller, already solved problems mashed together. And 4, once you find that pattern, you can use it to build a truly elegant and efficient solution. And that kind of leaves us with one final thought. Think about a big, complicated problem in your own world right now. Can you apply this method? Can you find the n equals 1 version of your problem, start there, find the hidden pattern, and build your way up to a solution? Something to think about. Thanks so much for tuning in.